Hi, my name is Parekh. I go to Schreiber High School in Port Washington, New York, and my project was utilizing AI for categorizing wildfire origins through satellite image analysis. So you probably already know this just by looking up at orange skies last year and watching the news from time to time. But wildfires are a very big issue right now. Over the past 40 years or so, we've seen a steady increase in the number of acres burned by wildfires in North America. The reason for this is global warming, leading to more warm and arid conditions where wildfires thrive. In the long term, this risk has to be addressed by fighting climate change. But in the short run, we can work to reduce wildfire risk by studying the ignition of wildfires. So the USDA defines three different types of ignitions: natural, accidental, and arson. Natural fires are almost always caused by lightning and are thought to be an organic part of Earth's forest systems. On the other hand, accidental and arson fires are caused by humans. Therefore, it's much more feasible and productive to focus our risk reduction efforts in areas of high human risk rather than areas of high lightning natural risk. So my goal was to set out and create an AI model capable of determining which type of ignition an area is most susceptible to from a satellite image. So I'm not going to go too in depth with prior research, but there's three studies you should know about. The first one focused in southern France and created an AI model to determine the cause of wildfires when it was unknown. So essentially, in southern France, they're having an issue where many wildfires were coming from an unknown origin. So these researchers set out to create a model that could classify what the cause of the wildfire was after it had already burned. So this was a retrospective classifying model because it included post-fire statistics, stuff like the date when the fire occurred and the size of the fire, information that can only be obtained after the fire occurred. This study achieved about 70% accuracy, classifying into five slightly more specific subgroups than just human and lightning fires. The other two studies go into the trends found in areas of high human risk versus areas of high lightning risk. Areas of high human risk tend to have a higher density of road networks, which makes sense because if there's more roads, there's probably more humans and more chances for humans to start fires. The second study showed that human and lightning fires actually tend to differ in their fuel type, the type of foliage that's burned by these fires. So these are both potential pieces of information that could be derived from satellite imagery. So the best way for me to explain exactly what I did to you is by using a flowchart. So I had data from two sources. First was from the CNFDB, which stands for the Canadian National Fire Database. This is a database that contains information, tons of information about wildfires that occurred in Canada. Stuff like when fires occurred, where they occurred, how much they burned, and most importantly for this project, what was the cause of the fire? What was the ignition of the fire? The other source I had was a collection of satellite images from Quebec of areas that had previously experienced wildfires before the wildfires occurred. So I was able to create a coordinate matcher and kind of mesh these two data sets together. So I was able to label each image with the appropriate cause. So here are two example images. And the one you see on the left is an example human fire satellite image, and the one on the right is an example lightning fire satellite image. So you can see some of the trends we discussed earlier with a road in the human image, but no roads in the lightning image. Obviously, though, this is not a trend that's seen in all images. It just happens to be in these two that I selected. So what exactly are these images? Essentially, the researchers who compiled this data set looked at areas where wildfires occurred and turned back the clock to what the area looked like right before the fire occurred. So these are images of areas that experienced wildfires, but before the wildfire actually occurred. So I plotted the locations of each of these images with the yellow dots being lightning fires and red dots being human fires. And you can see many more human fires towards the southern border of Quebec, which makes sense because where there's more humans, there's probably going to be more human-started wildfires. So after I matched up these coordinates, I ran the images through something called NumPy Data Prepper to get them in the right format for my convolutional neural network. So what exactly is a convolutional neural network? A CNN is a type of AI model that is very good at finding patterns in image data. It's specifically designed for images, while lots of other AI might be designed for numerical text data. CNNs are used for image data, so they're a great choice for this project, which uses satellite imagery. So what I did with these models is I created them and then showed them about 16,000 images that were labeled. I told them, okay, this image is a human fire, or in this image, a lightning fire occurred. And over time, my models got better and better at at figuring out what sorts of images are often human fires and what sorts of images are often areas where lightning fires occurred. So through about 20 different models, I kept tweaking something called hyperparameters in order to try to improve the CNN. Hyperparameters are basically the nitty-gritty of the model. How fast does it learn? How many layers does it have? How many nodes does it have for each layer? Stuff that you can tweak between models to try to improve your model's accuracy. So two main issues necessitated the bulk of these tweaks, those being overfitting and class imbalance. Overfitting is when the model learns to correctly identify patterns in exclusively the training set rather than across all images. So it gets super used to seeing the same training images over and over and thinks that the patterns it sees in the training images have to apply to all images, when in reality they could just be patterns exclusively in the training images. So the solution to this is called batch normalization, where the solution I chose was batch normalization and dropout layers, which basically disencouraged the model to hook onto these minute details that are only seen in some images in the training set. The other issue was the class imbalance, which is a bit funnier. I had many more images in my set that were lightning fires than human fires, so a local minimum was created. What this means is that whenever the model wasn't sure, it would always guess lightning, 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 because there are simply more lightning fires than human fires, so it had a better chance of getting it right if it guessed lightning. Solution was a class balancer, where I basically just evened out the data set, so this wasn't a problem. So the results, my best model achieved the training accuracy of 92% and a testing accuracy of 73%. The testing accuracy is what we really care about. That's the number that explains how accurate is the model when it's when it's shown an image that's never seen before. And 73% I was very happy with. It's moderately high, and the model is definitely seeing these trends in these images, which is great to see. What you see on the right is my final model architecture, which is basically the structure of the model. You can see some of the batch normalization layers, which work to reduce overfitting. So like I said, 73% accuracy is moderately high, and I was very happy to achieve it. The most similar paper that I talked about from Southern France achieved an accuracy of about 70%, but into more specific subgroups. So the reason why my study is still important, despite this other study, is because my study was a proactive forecasting model rather than a retroactive classifying model. What this means is that my model only takes in data from before fires occurred, so it can be used to forecast and allocate risk mitigation resources. While the other model is just for classifying, which is also an important function, but distinct from my own. The largest limitation on my model's accuracy was the number of images available for training, and in the future research, if we could train on more images, accuracy would probably increase. So it's important to, again, be able to tell which type of fire and areas at risk for, so we can allocate risk mitigation resources properly. The USDA defines 3 types of wildfire prevention: education, engineering, and enforcement. And it's very important that we allocate these types of resources in areas of high human risk where they'll be effective, rather than areas of high lightning risk where they won't be effective. So overall, the project goal was definitely accomplished, creating a moderately accurate neural network to predict wildfire origins. Here are my references.